Everything is made of atoms, and atoms are made of smaller things: protons, neutrons, electrons. Chemistry is the story of how these atoms get together, how they bond, how they react, how they form the stuff of our world. Water, rock, air, you. It's all chemistry. For a long time, we knew what happened in chemistry. We could mix things. We could observe reactions. We could write down rules, like two hydrogens and one oxygen make water. We got very good at this. We built an entire industrial world on these rules, but we didn't really know why. Why do two hydrogens and one oxygen stick together so well? Why not three hydrogens? Why does a bond form at all? Why does it have a certain length and a certain strength? Why is water a liquid, but the air around it is a gas? These are deep questions. The old rules of physics, the ones that work for baseballs and planets, couldn't answer them. Those old rules are called classical mechanics. They were figured out by people like Isaac Newton. They say that if you know where something is and how fast it's going, you can predict its entire future. It's a world of certainty, a world of smooth, continuous motion, and for big things, it works perfectly. But when you get down to the level of an atom, that world falls apart completely. Electrons don't behave like tiny planets orbiting a sun. If they did, they would constantly radiate energy and spiral into the nucleus in a fraction of a second. Every atom in the universe would collapse. So something was deeply wrong with the old physics. This is where quantum mechanics comes in. It's the new set of rules, the rules that govern the very small. And quantum chemistry is simply taking those rules and applying them to chemistry. It's the search for the fundamental why. It's about using the laws of the subatomic world to explain the world of molecules we see and touch. It's the physics of chemistry. The journey started in the early 20th century. Scientists were looking at weird things. They saw that hot objects didn't glow in the way classical physics predicted. They saw that light could knock electrons off a piece of metal, but only if the light had a certain energy. The old rules had no answers. A new idea emerged, the idea of the quantum. It means a packet. A discrete amount. Max Planck suggested that energy wasn't a continuous flow, like water from a tap. Instead, it came in tiny, distinct packets. You could have one packet of energy, or two, or three, but never one and a half. It was like saying you could only walk on stairs, not a ramp. This was a revolutionary, strange idea. But it worked. It explained the weird glow of hot objects. Then Albert Einstein took it a step further. He said light itself is made of these packets, these quanta. We now call them photons. This explained why light could knock electrons off metal. It wasn't about the brightness of the light, but the energy of each individual packet. And then the focus turned to the atom itself. Niels Bohr proposed a model of the atom where electrons could only exist in specific orbits, like planets stuck on designated train tracks. They could jump from one track to another, absorbing or emitting a packet of light in the process, but they could never be in between. This explained why elements, when heated, give off light only at very specific colors. Each color was an electron jumping between its allowed tracks. This was a big step, but it was still a bit clunky. It mixed old ideas of orbits with new ideas of quanta. The real breakthrough was a complete reinvention of how we see reality at this scale. A young physicist named Louis de Broglie had a wild thought. If light waves can act like particles, photons, maybe particles like electrons can act like waves. It sounded crazy. How can a solid little thing be a wave? But experiments proved him right. Electrons, when fired at a screen with two slits in it, created an interference pattern. The same kind of pattern you get when water waves pass through two openings. The electrons were behaving like waves, passing through both slits at once. This is wave-particle duality. It's at the heart of quantum mechanics. An electron isn't a particle, and it isn't a wave. It's something else, something our brains, built to understand a world of baseballs, struggle to grasp. It behaves like one or the other depending on how we look at it. This led to the master equation of quantum chemistry, the Schrödinger equation. Erwin Schrödinger realized that if an electron is a wave, there should be a mathematical equation that describes that wave. He found it. His equation is the foundation of almost everything we do in quantum chemistry. It's not a simple equation. It doesn't tell you where the electron is. That's the old way of thinking. Instead, it gives you something called a wave function. The symbol for it is the Greek letter psips. The wave function is a strange beast. It contains all the information you can possibly know about the electron. But it's information about probabilities. If you take the wave function and square it, it tells you the probability of finding the electron at any given point in space. It doesn't give you a neat orbit. It gives you a cloud of probability, a region where the electron is likely to be. We call these clouds orbitals. There are sorbitals, which are spherical. There are p orbitals, which look like dumbbells. These are the shapes that come directly out of the math of the Schrödinger equation. They are the standing waves of the electron around the nucleus. And here is the first major success of quantum chemistry. It explains the structure of the periodic table, the rows and columns, the patterns of reactivity. It all comes from how electrons fill up these allowed orbitals, these specific energy levels, according to the rules of quantum mechanics. But quantum mechanics has another layer of weirdness, the Heisenberg uncertainty principle. It says there's a fundamental limit to what we can know. You cannot know both the exact position and the exact momentum, which is related to speed and direction of a particle at the same time. The more precisely you measure one, the less precisely you know the other. This isn't a problem with our measuring tools. It's a fundamental property of the universe. The very act of looking at something so small changes it. So, quantum chemistry is built on these pillars. Energy comes in packets, particles act like waves. And our knowledge is limited to probabilities described by a wave function. It's a very different world from the one we live in. But it's the world molecules inhabit. The real challenge and the whole point of quantum chemistry is to apply these rules to molecules. A molecule is just a collection of nuclei and electrons, so we should be able to write down a Schrödinger equation for any molecule we want. Say, a water molecule. We put in the positions of the 1 oxygen nucleus and the 2 hydrogen nuclei. We put in the 10 electrons, and we ask the equation to solve for the wave function of the whole system. If we could do that, the wave function would tell us everything. It would tell us the total energy of the molecule. It would tell us the probability of finding electrons anywhere. From that, we could figure out the bond lengths, the angle between the 2 hydrogen atoms, how the molecule would vibrate, how it would react with other molecules. We would have a complete picture derived from the first principles of physics. Here's the problem. It's a huge, gigantic problem. The Schrödinger equation is incredibly hard to solve. In fact, it can only be solved exactly, by hand, for the simplest possible system, a hydrogen atom. 1 proton and 1 electron. That's it. As soon as you add a second electron, like in a helium atom, the equation becomes impossible to solve exactly. Why? Because the electrons don't just interact with the nucleus, they also interact with each other. They push each other away. Every electron is repelling every other electron all at the same time, while also being attracted to the nuclei. This creates a mess of interconnected movements. The math becomes a nightmare. For a simple water molecule, you have 10 electrons. That's an impossibly complex dance of repulsion and attraction. For a protein molecule with thousands of atoms and electrons, it's beyond comprehension. This could have been the end of the story, a beautiful theory that was useless in practice for any real chemistry. But it wasn't, because quantum chemists are clever, and more importantly, they are practical. If you can't find an exact answer, you find an approximate one. The entire field of modern quantum chemistry is the art of finding very, very good approximations. And we have computers to help us do the heavy lifting. The first and most important approximation is called the Born-Oppenheimer approximation. It's a simple, brilliant idea. Nuclei are thousands of times heavier than electrons. An oxygen nucleus is about 30,000 times heavier than an electron. This means electrons move incredibly fast compared to the slow lumbering nuclei. So, we can pretend the nuclei are frozen in place. We pick a spot for the nuclei, and then we solve the Schrödinger equation just for the fast-moving electrons in the static field of those fixed nuclei. Then we can move the nuclei a tiny bit and solve it again, and again. By doing this, we can map out the energy of the molecule at different arrangements of the atoms. We've separated the motion of the electrons from the motion of the nuclei. This simplifies the problem enormously, and for most chemistry, it works incredibly well. Even with this approximation, we still have the problem of all the electrons repelling each other. This is where computational methods come in. The first major method developed was the Hartree-Fock method. It's a mean field approach. Instead of trying to calculate the repulsion of every electron on every other electron at every instant, it does something simpler. It says, let's calculate the motion of one electron in the average field created by all the other electrons. It's like trying to predict a person's path through a crowded room. The exact way would be to track how they swerve to avoid every single other person. That's impossibly hard. The Hartree-Fock way is to say, on average, the crowd is just a general obstacle of a certain density, and calculate the person's path through that average blur. It's an approximation, a big one. But it was a starting point. It gave us a way to calculate orbitals and energies for real molecules. got the basic picture right. It could predict molecular shapes reasonably well. But it had a known flaw. It ignored something called electron correlation. Electron correlation is the fancy term for the fact that electrons are not moving in an average field. They are actively and instantaneously avoiding each other. They correlate their movements. If one electron zigs, the other one zags to stay away. The Hartree-Fock method misses this subtle dynamic dance. The energy it calculates is always a little bit too high because it doesn't fully account for how well the electrons can get out of each other's way to lower their repulsion. So the next generation of methods, often called post-Hartree-Fock methods, were all about fixing this problem. They are ways of systematically adding electron correlation back into the calculation. There are many flavors, like with acronyms like MP2 or CCSCT. These methods are more accurate than Hartree-Fock. They get bond energies and reaction energies much closer to what we see in experiments. But they come at a cost, a very high computational cost. A calculation that might take minutes with Hartree-Fock could take days or weeks with a highly accurate correlation method. And for large molecules, it's simply not possible. This created a dilemma. You could have a fast but not very accurate answer, or a very accurate answer that was too slow to be useful for most problems. For many years, quantum chemistry was stuck here. It was a tool for specialists working on small molecules. Then, in the 1980s and 1990s, another approach became popular. It's called density functional theory, or DFT. It's a completely different way of looking at the problem. Instead of trying to calculate the complicated, many electron wave function, DFT focuses on something much simpler, the electron density. The electron density is just a measure of how many electrons are likely to be at any given point in space. It's a function of just three coordinates x, y, z. The wave function, by contrast, depends on the coordinates of every single electron. For a water molecule with 10 electrons, that's 30 coordinates. The density is vastly simpler. The genius of DFT, based on theorems by Hohenberg, Kohn, and Sham, is the idea that the total energy of the molecule is uniquely determined by its electron density. If you can find the correct ground state electron density, you can find the correct ground state energy. This transforms the problem from finding a monstrously complex wave function to finding a relatively simple density. The catch: we don't know the exact mathematical formula, the functional, that connects the density to the energy. There is a perfect universal functional out there, but nobody knows what it is. So, just like with Hartree-Fock, people have to create approximations. They've developed hundreds of different approximate functionals with names like B3OYP or PBE. And here's the magic. Many of these approximate functionals work surprisingly well. DFT calculations can often achieve the accuracy of the more expensive post-Hartree-Fock methods, but at a computational cost that is much closer to the cheap Hartree-Fock method. It hit a sweet spot. It was fast enough and accurate enough for a huge range of problems. This is what turned quantum chemistry from a niche academic pursuit into a mainstream tool used by chemists, biologists, and materials scientists everywhere. DFT became the workhorse of the field. So what do people actually do with all this? What can quantum chemistry tell us? It can predict the structure of a molecule. You can give a computer a list of atoms, say 1 carbon and 4 hydrogens, and the software, using quantum mechanical calculations, will find the lowest energy arrangement. It will tell you that the carbon should be in the middle, with the 4 hydrogens arranged in a perfect tetrahedron around it, forming methane. It will predict the CH bond length to within a tiny fraction of an angstrom. It can predict how molecules vibrate. Every bond in a molecule can stretch and bend like a spring. These vibrations happen at specific frequencies. Quantum chemistry can calculate these frequencies. This is incredibly useful because experimental chemists can measure these frequencies by shining infrared light on a sample. If the calculated vibrational spectrum matches the experimental one, it gives strong evidence that you've made the molecule you think you've made. It can help us understand chemical reactions. A chemical reaction is the process of breaking old bonds and forming new ones. We can think of this process as molecules moving across a landscape. This landscape is called the potential energy surface. It's like a topographical map where the low values are stable molecules, reactants, and products, and the mountain passes between them are the transition states. The transition state is the highest energy point along the reaction path. It's the bottleneck. The height of this energy barrier determines how fast the reaction will go. A high barrier means a slow reaction, a low barrier means a fast one. And quantum chemistry is a unique tool for finding these transition states. You can't see them in a lab, they exist for only an instant. But with a computer, we can calculate their structure and energy precisely. This allows us to understand reaction mechanisms, to figure out step by step how reactants turn into products. This has huge practical applications. For example, in industry, catalysts are used to speed up reactions. So, a good catalyst works by lowering the energy of the transition state. Using quantum chemistry, we can simulate how different potential catalysts interact with the reactants. We can try to design a better catalyst on a computer before anyone even steps into a lab. This can save huge amounts of time and money in developing new industrial processes. Another major area is drug discovery. Many drugs work by fitting into a specific pocket on a protein called an active site. This blocks the protein from doing something that causes a disease. To design a good drug, you need a molecule that binds very tightly to that active site. Quantum chemistry can calculate the binding energy between a potential drug molecule and the protein. Computational chemists can screen thousands of candidate molecules virtually, predicting which ones are most likely to be effective. The most promising candidates are then synthesized and tested for real. Material science is another field that has been transformed. Want to design a new material for a solar cell? You want a material that is good at absorbing sunlight and then separating the resulting electron to create a current. We can use quantum chemistry to calculate the electronic properties of new hypothetical materials. We can predict their color, their conductivity, and their efficiency as a solar cell. This allows us to search for promising new materials in a computer rather than through slow and expensive trial and error in the lab. It's the same for designing better batteries, lighter and stronger alloys, or more efficient LEDs. Quantum chemistry even reaches into astrophysics. When astronomers point their telescopes at distant interstellar clouds, they see the spectral fingerprints of molecules. To figure out what molecules are out there, they need a reference library. Quantum chemistry provides that. We can calculate the expected spectrum of a weird, unstable molecule that might exist in space, but is hard to make on Earth. If that calculated spectrum matches what the telescope sees, we've discovered a new molecule in space. Of course, the field is not standing still. There are still major challenges. The biggest one is still the trade-off between accuracy and cost. While DFT is powerful, it sometimes fails. For some strongly correlated systems, where the simple picture of electrons and orbitals breaks down, DFT can give completely wrong answers. The more accurate post-Hartree-Fock methods are still too slow for large systems. So, one big push is to develop new methods that are both accurate and efficient. Another is simply to use more powerful computers. The supercomputers used for these calculations are some of the biggest in the world. As computers get faster, the size of the problems we can tackle grows. A calculation that was a PhD thesis 30 years ago can now be done on a laptop in an afternoon. Today's supercomputer calculations on systems with thousands of atoms will be routine in the future. And there are new frontiers. One of the most exciting is the connection with machine learning and artificial intelligence. We can use traditional quantum chemistry methods to generate huge amounts of data about molecular energies and properties. Then, we can train a machine learning model on this data. The model learns the complex relationship between a molecule structure and its energy. Once trained, the AI can predict the energy of a new molecule almost instantly, far faster than the original quantum calculation. It's a way to leverage the accuracy of quantum mechanics at a much lower computational cost. The ultimate dream, though, is quantum computing. A classical computer stores information as bits, which are either 0 or 1. A quantum computer uses qubits, which, thanks to the weirdness of quantum mechanics, can be 0, 1, or both at the same time. This allows them to perform certain types of calculations exponentially faster than any classical computer ever could. And it just so happens that one of the problems they are perfectly suited for is simulating other quantum systems. The idea is to build a computer that itself operates on the laws of quantum mechanics to solve the equations of quantum mechanics. A quantum computer could, in principle, solve the full Schrödinger equation for a complex molecule without any of the approximations we are currently forced to use. This is still a long way off. Building a useful, large-scale quantum computer is one of the biggest scientific and engineering challenges of our time. But if and when it happens, it will completely revolutionize quantum chemistry. We would be able to design catalysts with perfect efficiency, create new drugs with unparalleled precision, and understand chemical processes with a clarity we can currently only dream of. In the end, quantum chemistry is the bridge between the strange probabilistic world of subatomic particles and the tangible world of chemical reality. It starts with the fundamental question, why? Why do atoms bond? Why do reactions happen? The answer lies in the bizarre rules of quantum mechanics. The path to that answer is blocked by impossible mathematics. So, the practice of quantum chemistry is the art of the clever approximation, the powerful algorithm, and the massive computer. It's a field that lets us see the invisible dance of electrons that shapes our world, and increasingly gives us the power to choreograph that dance ourselves. It is the instruction manual for matter, and we are finally slowly learning how to read it.